You walk up to a lab airlock. A proximity sensor reads your presence, and heavy mechanical seals immediately snap open. We expect our physical actions to translate into digital commands instantly. We tend to assume this responsiveness is a built-in feature of modern computing. You plug a piece of hardware into a system, and the data simply appears on a dashboard. This diagram shows that translation. Getting a voltage reading onto a web browser meant passing data through a sprawling chain of software. A Python script reads the hardware, hands it to zero-MQ, passes it to Node.js, and finally to a React frontend. Every single one of those handoffs exacts a toll. You spend CPU cycles, you allocate memory, and burn time just to serialize and deserialize the exact same piece of data over and over. In high-stakes environments, the cost of that translation is physical. If an industrial manufacturing robot is swinging at high velocity, a 50-millisecond lag in processing a proximity sensor dictates whether a machine shuts down safely or crashes into an obstacle. Architectures built to handle high-volume web traffic are often dangerously slow for real-time physical instrumentation. To solve this, William L. Weaver, an engineer with 30 years of experience in advanced laboratory settings, stripped away the middleware to create the Compass stack, an architecture optimized entirely for immediacy. The journey of this data starts at the very edge of the network, typically on an 8-bit microcontroller like an Arduino Uno. This is a chip with a tiny fraction of the processing power of a smartphone, constrained to just 2 kilobytes of memory. The industry standard method for managing timing on these small chips is a command literally called delay. You instruct the processor to turn on an LED, delay for 1,000 milliseconds, and then turn it off. This diagram illustrates why that method is a mind killer for a processor. The delay command forces the CPU to stop evaluating code and simply count clock cycles. During that countdown, the chip is completely deaf to the outside world. If a user sends a command during that pause, it piles up at the barrier and is entirely ignored. Instead of halting the processor, the Compass methodology tracks time using independent hardware timers, internal registers that tick away regardless of what the CPU is doing. The main code runs in a continuous loop, quickly checking the time to see if an interval has passed. Every single incoming signal is caught the moment it arrives. By writing code that never stops to wait, the microcontroller transforms from a sequential task runner into a highly vigilant sentinel. It continuously monitors physical sensors and digital inputs without dropping a single critical command. Once the data leaves the microcontroller, it travels over a USB connection to the server. In Weaver's setup, a rock-solid Debian Linux workstation. For years, developers faced a severe dilemma here. Python was the best language for reading hardware serial ports, but Node.js was much better at managing incoming web traffic. So developers ran both, forcing 2 entirely different runtime environments to communicate. Modern frameworks have removed the need for that compromise. Python now supports native asynchronous execution, meaning a single, unified backend can process hardware inputs and serve web traffic concurrently. This diagram shows how that routing works in practice. The system assigns a background thread strictly to monitor the physical hardware port. Whenever new data arrives, it drops the information into a queue for the main asynchronous loop, which is busy serving web pages. Neither task blocks the execution of the other. Processing the data efficiently is only half the problem. The traditional way to send this data to a browser is HTTP polling. This forces the browser to repeatedly ask the server for the latest sensor value. Each request carries heavy text headers, requiring a full network handshake, often yielding the exact same stagnant temperature reading. To eliminate that drag, Weaver replaces polling with WebSockets. A WebSocket establishes a single, persistent two-way connection. The browser stops asking for updates. Instead, the server pushes the data down an open pipe the exact millisecond it arrives from the hardware. Combining an asynchronous Python backend with a persistent WebSocket pipeline completely strips out the network overhead. The server pushes data to the user at the exact speed the hardware collects it. The final stop for this data is the user interface, rendered locally inside a web browser. In contemporary software development, the immediate reflex is to load in a massive front-end framework, like React or Vue, to track application state and calculate updates to the document object model, the structural code of the web page. Pushing a high-speed stream of raw sensor data through those abstraction layers requires complex calculations just to draw a line on a screen. If the time series data comes in fast enough, the browser will literally start to stutter under the computational load. Weaver opts for what he calls the path of the ranger. He discards the heavy frameworks entirely, relying strictly on native vanilla JavaScript and an HTML5 canvas to build the interface. Writing the code in the browser's native language creates a direct mechanical linkage. The JavaScript simply listens to the open WebSocket and draws the data on the screen the moment it arrives, without any intermediate build tools or translation steps. By discarding complex front-end software, the result is a highly responsive, lightweight dashboard. The charts update with buttery smooth precision, visually matching the speed achieved by the backend. Every layer of this architecture is aligned to remove friction. You have a vigilant microcontroller tracking the physical world, an asynchronous server processing the data instantly, and a native interface displaying it without hesitation. Curious, what is particularly striking about this highly disciplined design is how it was created. Weaver developed this minimalist architecture through extensive conversations with an advanced large language model. There is a widespread anxiety in software development right now that AI coding assistants will flood systems with bloated, copy-pasted middleware because it's incredibly easy to generate. But Weaver applied the tool in the exact opposite direction. He used the AI as an architectural sounding board. Instead of generating volume, he leveraged the language model to test logic, cut through the noise, and identify the most direct path between the hardware and the user. As the physical and digital worlds converge, maintaining true responsiveness requires extreme precision. Engineering elegance and the true utility of artificial intelligence lies not in adding complex software layers, but in ruthless subtraction.